Alright, this was a test on exponential functions. I'm going to ask you to go ahead and put your pencil down, watch the video, learn how to do it, and then go back and do it yourself. Please do not watch the video with a pencil in your hand. Problem number one. When you're trying to graph exponential functions and you're not allowed to use a TI-30 XS multi-view, you need to pay attention to whether or not there is an A value. In case you're wondering, what is this A value of which you speak? This is what I'm talking about. We often look at the basic model of an exponential function this way. A times b to the x minus h power plus k. Of course, the parent function is just this part right here, b to the x. Now everything else is a transformation to the parent function. So when I talk about the a value, I'm talking about this number in the front. And as far as graphing it, we're going to set up a table of values, but listen to me carefully. If there's an a value, in this case 2, you're going to want to use a 3-column chart. If the a value is 1, in other words, if there's no visible a value, you're going to use a 2-column chart. So for problem number 1, we are going to use a 3-column chart. And we can just always start off with these same 5 center values, -2, -1, 0, 1, 2 for the x values. Now the first column we're going to do will always be the parent function, so I will put b to the x power, you know, just like, because that's always the part of the model that represents our parent function. So I'm talking about 3 to the x power is what we're doing here in this first column. Alright, so when I talk about 3 to the x power, I'm talking about this. You know, these are my x's, so I'm talking about 3 to the -2 power, 3 to the -1 power, 3 to the 0 power, 3 to 1 power, and 3 to the 2 power. Alright, b to the x, and 3 is my b. So this would be 1 over 3 to the 2nd power, because that negative exponent drops you down. But that is 1 over 9. So that's why, switch colors. So that's why I have 1 over 9 right here. And similarly, 3 to the -1 power would drop down and just be 1/3. Alright, anything to the 0 power is just 1. Then of course 3 to the 1 power is 3. And 3 squared is 9. So these are the values of the parent function. Now because there is an a value though, before we start graphing things, we need to go ahead and multiply everything by this a value. So let's take our b to the x power and multiply all these by 2. Alright, so I'm just multiplying everything by 2. Alright, so that's just going to give me 2 over 9, and 2 over 3, and 2, and 6, and 18. Alright, and this is a b times b to the x power that we just did. So that's the third column that I was talking about. Now, what we have not done yet was we haven't done anything with the -5, and we'll do that later. But we will go ahead and graph this third column. So at -2, we're up 2/9. So 2/9 is just barely off the ground, so it's almost on the line. And okay, at -1 we're at 2/3, so that's 2/3 of the way up a square. At 0 we're at 2, and then at 1 we're at 6, and then at 2 we're at 18, which is like way up here somewhere. Alright, we will not draw the curve at this point, because this is just the skeleton. We haven't done the minus 5 yet. Now, the minus 5 comes in right now. This k value, where the minus 5 is an up or down shift. If it's positive, it will be up. If it's negative, it will be down. So this minus 5 represents a down shift of 5 units. So what we will do is we will move these points down 5, and then that will be the real graph. Okay, and I think I will do that in, I'll go ahead and do that in blue. Alright, so if I move these down 5, so 1, 2, 3, 4, 5. Okay, and then the next one was at 2/3. Alright, and the next one was here. And the next one, 1, 2, 3, 4, 5. Okay, and this is up here at 18. If I move it down 5, it should be at 13, which is still off the chart, but you know, let's say it's about there. Alright, now this blue one is the one we'll actually graph, but we do need the asymptote. Now looking at the equation, we know the asymptote is -5. Alright, this k value is always the asymptote. I should say y equals -5. So let's draw the asymptote, dotted line. Alright, so there's the asymptote. Then we will draw the curve to the best of our ability. It's already basically on the line when we get to here. In our minds, we know that it gets closer and closer but never touches. But alas, our ink and even our pixels have thickness, so when we try to draw this, it's going to look like we're on the line, and we'll just have to use our imaginations to know that we're not touching. Okay, so we just draw this as best we can, and you guys will never know how tough this is to do with an electronic pen, but hopefully it's easier in your life where you live with a pencil. Alright, that's the best I can do. So that would be a full credit graph. Do not stop, don't let your graph stop short. Stretch it all the way out to the edges of the grid. Alright, so that was problem number 1. Now, like I mentioned, for problem number 2, there is no a value. I mean, a value is 1. So when that happens, we're not going to need an extra column to multiply by a, because there is no a value. So we'll just have the first two columns, and we'll graph the parent function. So let's go ahead and make our two columns. Okay, so this is -2, -1, 0, 1, and 2. We'll just always use those same values. Now we are dealing with, let me delete some of this stuff. Alright, when we say b to the x power here, alright, the parent function, we're talking about this part. So we're talking about 1/4 to the x power, alright? We're not doing the -3 or the +4 yet. That'll be our shifting that will come later. So we're talking about doing 1/4 to the -2 power, and 1/4 to the -1 power, and 1/4 to the 0 power, and 1/4 to the 1 power, and 1/4 to the 2nd power. Now when you have a fraction and a negative exponent, you do the reciprocal. So I will do, this will become 4 to the +2 power, which is 16. Again, negative exponent on a fraction, do the reciprocal. 1 over 4 becomes 4 over 1, which is just 4. And then anything to the 0 power is 1. 1/4 to the 1 power is just 1/4. Alright, 1/4 squared, you can just square each of these separately. So 1 squared is 1, and 4 squared is 16, so that's 1/16. Alright, so let's go ahead and graph these, alright, even though this is not the real function, it's not the final function. So negative 2 is at 16, which is off the charts, but I will fake it, alright. So negative 2 is at 16, so that's like 1, 2, 3, 4, 5, 6. You know, it's about somewhere about like there. At negative 1, we're at 4. At 0, we're at 1. And then at 1, we're at 1/4, which is pretty low. But at 2, we're at 1/16, which is so low that it's going to appear to be on the line, even though it's really a tiny bit above, but we don't have the resolution to show that. Alright, so these are the dots that are forming the skeleton. But we will not draw the curve through them because this is not the real deal. For the actual function, we will have to do these transformations. Now remember, the k value here is an up or down shift. Positive up, negative would be down. Now what's going on here in the exponent is a left-right shift. And it's kind of the opposite of what you might think. So like a -5, for example, will actually be a shift to the right 5. And a positive 5 would go to the left. So it's kind of backwards. Okay, so this negative 3 that you see is really a shift to the right 3. And this positive 4 is up 4. So we need to take all of these skeleton points and move them right 3 and up 4. So this one is already off the chart, so that's going to be so far off the charts that I'm just going to ignore it from now on. But I'll do this one though. So right 3 up 4. So 1, 2, 3, 1, 2, 3, 4. Okay. 1, 2, 3, 1, 2, 3, 4. Okay, 1, 2, 3, 1, 2, 3, 4. And I know the next one would be like here. Okay, the asymptote is at 4, so let's go ahead and draw in that asymptote. Alright, and then we will do our best to draw this curve. It's already looking like it's on the line here, so from here on it's going to definitely appear to trace the asymptote. Alright, until it gets to here. Alright, got a little crazy in there. Alright, your graph should look something like that. It got a little messed up in the middle, but I'm not going to redo it. You get the idea. And that is how you do that. Alright, that's number 2. Alright, for number 3, we're supposed to give these characteristics for problem number 2. So hopefully you didn't mess up problem number 2, because then that's going to cost you number 3 as well. Well, maybe not, because the domain is really always the same for these exponential functions. It's always negative infinity to positive infinity. And the reason is we know that domain represents how far the graph goes from the left to the right. You know, it's the x values. And they always go, exponential functions always go left and right forever. So there's the domain. Now the range, on the other hand, has limits. It does not go up and down forever. It goes up forever, but in this case, it levels out at the asymptote. So that's a lower bound, a lower limit. So the range, which we will always give in the order of least to greatest, which in this case means bottom to top. The bottom of this graph is here at the asymptote of 4. and we will use a round parentheses to show that we don't actually include the asymptote, which you never reach. So 4 to infinity would be the range. Of course, the horizontal asymptote itself, we see it's here at 4 because of that, but we don't just put 4, we put y equals 4. Alright, so that's number 3. Genius. Alright, we talked about this a little bit. The one thing I didn't mention when we looked at this page was if the a value is negative, like kabam, then that would be a reflection over the x-axis, as opposed to not having a negative. Okay, I'm mentioning that because of that right there. So we've got these two transformations. This negative in front is going to be a reflection over the x-axis. And of course the -1 is a left or right shift. Specifically, it will be a shift right 1 unit. Okay, looking at B here, we've got the two transformations. This 1/3, because the a value is less than 1, that is a vertical compression by a factor of 1/3. Alright, and of course the -4 is a shift down 4 units. Alright, similarly, we have this a value here again. Because it is bigger than 1, this is going to be a vertical stretch by a factor of 3. Aw, it needs to fit. Okay, vertical stretch by a factor of 3. And what else we have going on here? Then we have the +2, so that'll be a shift left 2 units. And then we've got the +5, so that'll be a shift up 5 units. Alright, so that is it for number 4. Well, I looked and looked, but I don't see a number 5 or 6, so not sure what's going on there. Hopefully there's not 2 missing problems that we were supposed to have done. Anyway, whatever, number 7. So we're going to solve this equation. We need to get this expression by itself, so what you want to do is add 6 to both sides first. So that's going to give you x plus 4 to the 5th power is equal to 32. Now, to get rid of this 5th power, we will use the 5th root. Okay, so we will do the 5th root of both sides like this. Alright, we don't need to do plus or minus because it's an odd root. So that is going to give us x plus 4, alright, because the root and the power cancel out. And then the 5th root of 32, I know that it is 2, but if you did not know that, you could use a chart like this one. 5th root of 32 is 2. Alright, and then we just subtract 4 from both sides, and we get x equals -2. Alright, if this were a radical problem, you know, with some sort of a root in it, we would have to check this answer to be sure, but we don't. Now, so I guess I should put that on the line. So x equals -2. And then number 8. Same thing, before I do anything else I need to get this radical by itself. So you should do minus 8 on both sides. So that is going to give me the square root of x plus 5 is equal to negative 4. Now, to get rid of the radical, I will square both sides. So I'm going to square this and square this. Notice how I put the parentheses around it because I'm squaring, I want to do negative 4 times negative 4. So anyway, I'm going to get x plus 5 is equal to 16. And then when I subtract 5 from both sides, I get x equals 11. Okay, but I have a feeling that this solution, so-called, will not actually work. And I get that feeling from this line right here. Before I squared it, we had a radical equal to a negative number. And that can't happen. There's nothing you can take the square root of that's going to give you a negative number. So we really knew this was going to be no solution. But we will prove that by plugging this back in and watching it make a false statement. So we will do this. Check. And you should always check when there's a radical in the problem. So this would become the square root of, I'm checking 11, square root of 11 plus 5 as I plug it in, and then plus 8 is supposed to equal 4. Alright, this 4 should stay here the whole time. Of course, 11 plus 5 is 16, so I've got the square root of 16 plus 8 is equal to 4. So that's 4 plus 8 is equal to 4. So that's 12, which is not equal to 4. Boo! So that means that this is extraneous. Alright, that's extraneous. And since that was the only solution we had, then we will go ahead and say no solution. Alright, let's find number 9. There it is, there it is. Now, when you have variables in the exponent, the key is to make the bases the same. Now, some kids mistakenly try to write 27 as 9 to some sort of a power. 9 squared is 81, so there's no way you're going to use a base 9. Instead, you have to turn both of these into a base 3. 9 is 3 squared. Alright, so I can replace 9 with 3 squared. 27 is 3 to the third power. All of this you can get off of your handy dandy exponent chart. No, don't save. Yeah, so you see the 9 and the 27, they're both base 3. 3 squared, 3 to the third power. Why is it so small? Yeah, 9 and 27. Anyway, but so you still have the 4x, which you will put in parentheses and just put it next to the 2. And you still have the 3x minus 2, same deal. Okay, so that means I have 3 to the 2 times 4 is 8, so 8x. And here I have 3 to the. And I need to distribute, so that's going to be 9x minus 6. Alright. Now, if the bases are the same in this equation, then the exponents would have to be the same. So logic tells us that 8x must equal 9x minus 6. We're not canceling out the 3's. This is logic. So now we will subtract 9x from both sides. Alright, so that's going to leave us with negative x, like negative 1x, is equal to negative 6. And dividing both sides by negative 1 gives us x equal 6. Okay, so that is the answer for number 9. Alright, number 10 then. Alright, so the first thing you want to do is get rid of this fraction. And you can do that simply by multiplying both sides by 2. Alright, these 2's will cancel out, and you're on your way. So you'll still have this 8 to the 2x plus 1 power. Alright, 2 times 256 that's 512. Alright, now just like before, we need like bases. See the 8, see the 512, look at your chart. Alright, see the 8, see the 512. Both of these are base 8. Alright, so 512 is 8 to the third power. So let's do that. So I've already got my base 8. So 8 to the 2x plus 1 power, and this is 8 to the third power. Since the bases are the same, the exponents must be the same. So 2x plus 1 must equal 3. Subtract 1 from both sides, we have 2x equals 2. Divide both sides by 2, and you have x equals 1. Alright, that is the answer to number 10. Number 11. When I watch students review, I saw a lot of kids trying to do the third power like immediately. That does not work. Alright, you can do the third power to both sides of an equation, but you can't just do it twice on one side. So those kids had not done their homework Burton style. Because we have learned that we need to separate these. We need to have one radical on opposite sides of the equation. And we will accomplish that by adding the cube root of 2x plus 7 to both sides. Alright, so these will cancel out. So you will wind up with the cube root of 4x minus 1 equals the cube root of 2x plus 7. Now you can cube both sides. Alright, and poof, that cancels out the radical, so you will have 4x minus 1 is equal to 2x plus 7. Alright, when you have x's on both sides, subtract one of them to get them together. So that'll give me 2x minus 1 is equal to 7. Then let's add that 1, so that'll give me 2x is equal to 8. And then divide by 2. Which will give me x equals 4. Alright, now this might or might not be the solution. We're going to have to check because this is a problem that involves radicals. So x equals 4. Let's take a look. So I will do my check in another color. Alright, so I'm checking, what did we say, 4? I'm checking 4 out. So plugging 4 in, I would have the cube root of 4 times 4 minus 1 minus the cube root of 2 times 4. Plus 7 equals 0. So this would give us the cube root of 16 minus 1, alright, minus the cube root of 8 plus 7. So this is going to be the cube root of 15, and this will be the cube root of 15. Alright, the cube root of 15 minus the cube root of 15 is 0. So 0 equals 0, so it checks out. All right, fantastic. Yeah, 11 has an answer of x equals 4. Okay, number 12. Alright, unfortunately I'm going to have to erase my beautiful check now. Alright, time for number 12. We need to get this whole parentheses situation by itself. So the first thing you want to do is add 7 to both sides. Those are gone. So that will leave us with 2 times 4x minus 12 to the 3/5 power is equal to 16. Then you want to divide by 2. Got to get rid of that 2 before we do anything special. So we will divide both sides of this equation by 2. These 2's cancel out, and that is going to give me 4x minus 12 to the 3/5 power is equal to 8. Now, the easiest way to deal with this fractional exponent is to do the reciprocal power on both sides. So I have 3/5, so I'm going to raise this to the 5/3 power on both sides. 5/3 power. That allows me to cancel these out. Okay, so on this side I'm just going to have 4x minus 12, plain and simple. Now over here I've got 8 to the 5/3 power. It would be useful to convert this to the other form. So you know what, off to the side, I think I'll break out the green. I'm going to take this and I'm just going to do it off to the side. Okay, so I'm talking about the power over root. So that 3 in the denominator means it's the cube root of 8. Alright, that 5 in the numerator means to the 5th power. Alright, the cube root of 8 is 2. So that's going to be 2 to the 5th power. And 2 to the 5th power is 32. If you didn't know any of these things, you can get it off the chart. Right? The cube root of 8 is 2, and then 2 to the 5th power is 32. Alright, so that means this thing is really 32. So we can just bring that on down and continue with the problem. So, time to add 12 to both sides. So that'll give us 4x is equal to 44. And then we would divide both sides by 4. And that gives us x equals 11. Alright, which is probably the answer. Now this problem did involve radicals, because right from the beginning we had this 5th root. Alright, and 5th root is a radical. So you should check your answer as I am going to right now. Let's see, I'll just do this right here. So I am checking. I'm checking 11. So that would make this 2 times 4 times 11 minus 12 to the 3/5 power, right? Yeah. Minus 7 is equal to 9. So that's going to give us 2 times 44 minus 12 to the 3/5 power minus 7 equals 9. Okay, 44 minus 12 is 32. So this will give us 2 times 32 to the 3/5 power minus 7 is equal to 9. Now 32 to the 3/5 power is what we'd have to do next. I will just do that off to the side again though. 32 to the 3/5 power means, alright, I've got my 32. The 5th denominator means a fifth root. Okay, the 3 in the numerator means cube that. Now the fifth root of 32 is 2, and 2 to the third power is 8. So that means this right here has a value of 8. So I have 2 times 8 minus 7 is equal to 9. So that's 16 minus 7 is equal to 9. Oh wait, no, yeah. And 16 minus 7, of course, is 9. So I've got 9 equals 9, so it checks out. So that's what we thought. Okay, we get to make up our own function, man. That's awesome. Create an exponential function that is vertically compressed compared to the parent function, 3 to the x power, and has a range of -5 to infinity. Well, vertically compressed, we need an a value that is less than 1 if it's going to be compressed. So, so I've got f of x equals, now the parent function is this 3 to the x power. Okay, so I'm just going to put parentheses around it to make the a value stand out. So, for example, I could put a 1/2 right here. But, you could have anything that's less than 1. 1/2, 1/4, 2/3, 0.7, whatever you want. So that takes care of the vertically compressed part. Now the part about having a range from -5 to infinity, this is just an indirect way of giving us the asymptote, because you know how these things work. If this was the axis, and imagine that we had an asymptote at -5 like this says. So 1, 2, 3, 4, 5. So the asymptote would be down here like this. Alright, and if the asymptote's down there, then that means the graph is, flattening out here and this like going up like this. So that means the range, bottom to top, would be -5 to infinity, just like we want it. Alright, so the range is always going to involve the asymptote, so this is just a fancy way of giving us the asymptote of -5, which goes right here in the equation. So you definitely needed a -5 right here, and in front you could have anything less than 1. Put a note to myself. Anything less than 1. Alright, that's number 13. Oh, I got a little multiple choice going on. Okay, well, we have learned that if you have a negative power on a fraction, the easiest thing to do is to do the reciprocal and make it a positive exponent. So this would quickly become 243 over x to the 5th power, and then that's to the 2/5 power. Now, when you have a power on a fraction, really what you're doing is you're doing this power to each thing separately. So in other words, I'm doing 243 to the 2/5 power, and I'm doing x to the 5th to the 2/5 power. Now down here, when you have a power to a power, you multiply. So this would be like 10/5. But 10/5 reduces down to 2. Or you can do it the way I do it and just cancel out these 5s. So the denominator is definitely going to just be x squared. Okay, now the numerator, remember this, which I think I'll just do off to the side, Alright, I would use our radical form, so power over root. So this is the 5th root of 243, and then that whole thing is going to be squared. Alright, so 5th root of 243. Let's look at the chart. 5th root of 243 is 3. Okay, so this part in here is simply 3, and then that 3 squared is 9. Okay, so that's why we're going to have a 9 right here. So it's just 9 over x squared, which I can see right there is d. Okay, fantastic. So that was number 14. Number 15, the determinant. Now, this is not a reverse negate situation. That's when we're doing the inverse. This is just the determinant. The determinant is the down diagonal minus the up diagonal. That is all. Alright, so the down diagonal, 5 times negative 3, that is negative 15, minus the up diagonal. Alright, the up diagonal is positive 32. So we're just talking about negative 15 minus 32. Okay? So since you don't have your TI-30XS multi-view, you have to know a little bit about arithmetic. So doing negative 15 minus 32 is the same thing as doing negative 15 plus negative 32. So we are really going to just add these numbers up, and then it'll just be a big old negative number. So that's going to be 47. So negative 47, which I can see right there is C. Okay, great. That's number 15. Number 16. Let's do what we do. You see that x to the 0 power, alright? X to the 0 power is 1. Not x, 1. So basically that's gone. So forget about that. Now, I see this negative exponent right here tells me that this is going to have to go to the other side of the fraction. So it's going to come up here and become z squared. Alright, so that we just moved that. That's gone now. It's up here now. And that was the only one. So now we can go ahead and put this whole thing together. Okay, so number wise, I've got 3 times negative 3 times 4, so that's negative 12 over 2. Okay, so that's the numbers. How about x's? That x is gone, so all I have is x to the 3rd power, so that's going to stick around. So what about the y's? Alright, I've got y squared over y. So that y is going to cancel out one of those y's and leave a y up top. What about the z's? Well, all the z's are up here, and there's 3 of them, right? Z squared, z, that's a total of 3. So that would be z to the 3rd power. Okay, 2 goes into 12 6 times, so that means we're going to have negative 6 y z to the 3rd power over x to the 3rd power. Okay, and there it is, B. Alright, and number 17. So to get rid of this radical, we need to square it, but we have to be careful about how we do that, because when we square this side, we're squaring a binomial. Okay, so that means on this side, we will have the x plus 5, alright, because the radical goes away. But over here, we need to FOIL this, or double distribute, as I like to call it. We need to do x plus 3 times x plus 3. So we're doing this stuff, alright? We're multiplying it all out. So on the left, we still have x plus 5, but x times x, that's x squared. X times 3, that's 3x. Repeat. Alright, 3 times x is 3x. 3 times 3 is 9. So that's x plus 5 is equal to x squared plus 6x plus 9. Alright, I see the x squared and the x, so I can't just get x by itself, so I'm going to wind up factoring or using the quadratic formula. But for right now, I'm going to subtract x from both sides. And you know what? I might as well subtract the 5 as well. Just line up your like terms. So I have 0 equals x squared plus 5x plus 4. This is easily factored. Alright, x squared can only be x times x. 4 is either going to be 2 times 2 or 1 times 4. Based on the fact that we need to get 5 in the middle, I'm betting on 1 times 4. Okay, inner we have 1x. Outer we have 4x. We're trying to get 5, so we could get that if these were both positive. And positive 1 times positive 4 is 4. So there we have factored it correctly. Alright, now to get the actual solutions, we set these equal to 0. So x plus 1 equals 0, and x plus 4 equals 0. Subtracting 1, subtracting 4, gives us x equals negative 1, and x equals negative 4. So these are our two potential solutions. But it's likely that at least one of them is extraneous, so we're going to have to check them. Okay, let's start with the negative 1. Check that. Alright, checking negative 1 would give us the square root of negative 1 plus 5 is equal to negative 1 plus 3. Again, the reason we know we have to check this is because there's a radical in the beginning, which sometimes causes problems. So, alright, so that's just going to be the square root of 4. Alright, and negative 1 plus 3 is 2, and the square root of 4 is 2. So it's 2 equals 2. So that checks out. That's great. Okay, so now let's go ahead and check. What was the other one? Negative 4. Okay, so let's check negative 4. So that would make square root of negative 4 plus 5 is equal to negative 4 plus 3. Well, negative 4 plus 5 is 1, so square root of 1. Negative 4 plus 3 is negative 1. I see the problem. Square root of 1 is 1. And 1 does not equal negative 1. So boo on that one. So that means that negative 4 here is extraneous. Okay, which means that x equals negative 1 is the one and only answer to number 17. Alright, and I believe that is it for this particular assessment. I think we handled our business. Alright, I hope this was helpful, And I hope you were not copying off me with your pencil as we went along. Guess I should have put this over here. F of x equals 1/2 3x minus 5. Make sure you can do all of these problems by yourself without any videos or anything. Alright, I will see you on the next video. Peace out.